Purple. Okay, physical science time. Today we are talking about use the kinetic molecular theory to explain states of matter. So we're talking about the kinetic molecular theory. Use kinetic molecular theory to explain states of matter. What are so we're talking about states of matter. Let's call it that. States of matter. What are the states of matter? What does it mean for something to be a state of matter? Solid, liquid, and gas. End of list. Plasma. Solid, liquid, gas, plasma. There are others. I'm aware of one called Bose-Einstein condensate. I'm aware of another one called superfluid, and there are more, but these are the ones we're going to talk about today. The state of matter is kind of like the condition, a particular kind of matter in relation to kinetic molecular theory, basically how its particles are behaving, how its particles are moving in space, how its particles are acting. So we use this idea of what's called the kinetic molecular theory. And the tenets thereof, the ideas contained within the kinetic molecular theory are almost, this is the right thing, this is the right thing, but not that. This is supposed to be a little thing that has like, it screws onto this. It has like a little nurple on the top, and this thing screws onto it, and it is in two pieces. So it's like a suction cup kind of, and it's a glass. It is a glass rounded dome. Let me draw you a little picture. It looked like this, and it has like a plate in there that has like a rubber ring around it that keeps it on, and then it has this little nurple on top that hose will go onto. Okay, yeah. Thank you, Miranda. Anyway, one thing that we understand from kinetic molecular theory, remind yourself that a theory is an explanation for how the universe behaves that all the evidence we have supports. So this theory, it's not how you use or how some people use the word theory to basically mean a hypothesis. Like you might say something like, I have a theory that it's going to be 75 degrees today. And that basically in the way you're using it means guess or hypothesis. But this, in science, it means that it's an explanation that all of the evidence supports. Kinetic molecular theory. So we can't see all the cases of every piece of matter in the universe. We can't observe all of them on the atomic level. But from those that we can observe, we understand that all matter is made of what? Atoms. Atoms. Particles. We'll put particles. Made of particles. All matter is made of particles. All matter is made of particles. Those particles are doing what? All the time. In every case that we can observe, and we can observe this. Yeah. The particles are in constant, all the time, random, all over the place, motion. And 3, the particles, if they're moving around all the time, and everything is made up of them, what must they sometimes do? Collide. The particles collide. Now, we had talked about in chapter 5, when we kind of first talked about this idea, that temperature relies on the speed and distance apart that the particles have. So we remember that higher temperature equals what about the particles? Yeah, more distance, and they're moving, higher speed. I'm going to put average in there, because remember, temperature is a measure of the average motion of the particles. Higher average speed of particles. And I'm glad this happened, but when we came into this room this morning, someone said, it's too hot in here. And it is for that person. And why? According to our science, according to physical science, according to the kinetic molecular theory of matter, what makes us feel like that is too hot? What is true of the particles that makes us feel like it's too hot? They're moving too fast, right? Our body is comfortable at a certain range of temperatures. Kind of a wide range. Your body itself, its temperature is almost always around 90 about 98 to 99 degrees Fahrenheit. But you're comfortable at a much wider range of temperature. In fact, 98 to 99 degrees Fahrenheit is not a comfortable temperature for your environment, right? You are comfortable at a range of temperatures. We like it to be about, what is it right now in here, Garrett? 69. That's fine. Nice. That's really fine. But somewhere between like 65 and 75, that's a comfortable temperature for us in degrees Fahrenheit. And if it gets hotter than that, well, these particles collide with us. We don't notice that. We're like, oh, the particles are really colliding today. But that is what it is. That's what temperature is. That's what we feel as hot, or conversely, what we feel as cold is when they're moving very slowly. And remember, the transfer of this thermal energy is called heat. So bearing in mind that these things are true, higher temp equals higher speed of particles, we're now going to talk about the states of matter. Which of these do you think, for a given piece of matter, let's say water, it's convenient to use water for this, which of these would the particles have the lowest energy? Solid. That have the lowest energy. The particles in a solid vibrate. They do move in constant random motion, but they're not going about. It's kind of like you right now in a relatively low energy state. Each of you, think of yourselves as kind of like atoms, is moving a little bit. Like I see your pins moving, I see your legs wiggling, I see your little faces move, and you understand that you are moving, but you're kind of moving in place. Other than Miranda, who's still looking for the thing I sent her to look for, you all you have motion, but you're moving in place. Okay, that's kind of what the particles are doing in a solid. The particles vibrate. The particles may be in a crystal lattice. That means a repeating pattern. We'll put a set repeating pattern. This would be like if you sit in the auditorium, the chairs are oriented. I keep using sound effects when I'm not using words, but you know what I mean. Like there's a row, and then there's a row behind that, and a row behind that, as opposed to if you're kind of sitting in this classroom or some other classroom where you're kind of dotted around randomly. You're not necessarily in strict rows. So some solids have a crystal lattice. That's what makes a solid a crystal, is if it has this repeating pattern. Not all solids. Other solids are called amorphous solids, but those particles may repeat, and if they do, that's called a crystal. I'm going to put that in parentheses. If they don't form a pattern, that solid is said to be amorphous. If we add a little bit of energy to this, probably in the form of heat, what will happen to these particles? The particles that were vibrating, what will they now do you think? Okay, they'll get faster. That's right. That's the first step. They will, if we add some thermal energy to them, they will get faster. But now instead of vibrating in place, if we add a little bit of energy to you guys, like there's a fire drill or something, you'll all get up and start moving around and kind of moving past each other, sliding past each other. Particles, I put slide past each other. So they move more than just in place. More than just in place. The particles slide past each other. If I draw an arrow over here, what are we doing as we go down this list? Increasing what? Yeah? Say it in a more basic science way. More basic. We're adding what to them? What very basic thing of the universe? Energy. Increasing energy for a given substance. Particles slide past each other in this case. The particles slide past each other, and that happens at what's called the melting point. The temperature where that happens, or the temperature when that happens, is called the melting point. Now get this. The melting point in degrees Fahrenheit, you know what it is for water? The melting point? Yeah, it's 32 degrees Fahrenheit. That's also the freezing point. Did you know that? It's both. It's the melting point. It's also the freezing point. So at this point, at this temperature, water exists as both a liquid and a solid. And in fact, a slush. And in fact, as long as both of those states are present in that environment, in that area, that water must be that temperature. So if you get a glass of ice water at a restaurant, that ice water, since it has both ice and water, must be 32 degrees Fahrenheit. It must be at that melting point and the freezing point together. The same thing with boiling water. If the water starts to boil, which we'll get to in a second when we get to a gas, but if the water starts to boil, both the gas and the liquid must be 212 degrees Fahrenheit. As long as both of those states are in one place, they have to be that temperature. That has to do with this idea of the heating curve of a liquid, which we will get to in a second. If we add more energy, the particles, instead of now sliding past each other, this is like, I'm trying to think of something that would really excite you guys. What even makes people happy? Nothing. Okay, good. This is like if something very mystical made you happy that we can't even identify. This is like if a gentle rocket came in here and gave everyone $1 million. And now the particles, it's a sad state of affairs when the only thing I can think of to make a group of freshmen happy is money. But if everyone got $1 million, we would probably, at least momentarily, be happy, right? Money doesn't buy happiness, but we would be pretty jacked if we all got $1 million. The particles bounce off of each other and the walls of their container. The particles bounce. You'd be like, whoa! You'd be running around the room, bouncing off the walls, as we would say. The particles bounce. But in physics, in this idea of the kinetic molecular theory, they're literally bouncing. It's not just a metaphor that they're bouncing off the walls. They're literally bouncing. They're bouncing, and we'll talk about that in a second, but in this one, they fill their container. Gases expand to fill whatever container they're in. Let me show you. I have some gas here. Do you see? The gas is contained in a container. Do you see the container of gas I have? What kind of gas is this? It's air. It's a mixture of oxygen and nitrogen and a little bit of carbon dioxide and a little bit of water. And this gas is contained in what volume? Approximately what volume would you say this is?
3 cubic centimeters.
It's a little bit more than 3 cubic centimeters, but I appreciate you trying to use the SI. Let's think about it compared to a gallon, because we're Americans. We'll say about half a gallon, right? That's a volume of gas. We got about half a gallon. Half a gallon. We would notice this a lot if instead of air this were filled with like perfume or something. But if I go like this, if I go like that, now where's the gas? Is it still just here? No. It's expand. It will, over the course of time, it will expand to fill this whole room, and since the window is open, it'll go out there too. Like I say, we would notice it if it was full of perfume or dog poop smell or something, but we would notice that smell would diffuse. We call that process diffusion. It fills its container because those particles have enough energy that they're bouncing all around. Is that true for my liquid? I have some coffee here. What shape is it right now? About what volume of coffee would you say I have in there left? There's probably more like a quarter of a cup. And what shape is it right now as I just hold it?
Coffee cup.
Yeah, it's coffee cup shaped. So the liquids have a definite volume, we'll say about a quarter of a cup for this, but no definite shape. It takes the shape of its container. The gas filled its container. It had both the volume and shape of its container. This has no definite shape. Now what shape is it?
Floor shape.
It's floor shaped. It's much flatter, right? Is it still a quarter cup of coffee? About. Whatever we thought it was before, it still is that. The volume is the same, but now it has the shape of its container, which is floor. Why don't you go clean it up with the beer? That's okay. That's okay. That's okay, girls. Yes, do grab a paper towel because I did make a little mess. Now a solid, I think you know where this is going, but this has a definite shape, right? Check it out. Is this a solid?
Yeah.
Yeah, there's some liquid in here, but this is, as an object, this is a solid. What shape is it? Marker shape. What volume is it?
3 cubic centimeters.
3 cubic centimeters, whatever. It has a set volume, right? It's not 3 cubic centimeters. Maybe 40 cubic centimeters. I don't know. But this has a set volume and a set shape. Now, same thing. What shape is it now? It's still marker shape. It does have a little bit of coffee on it, but it does have a definite shape and a definite volume. This is actually, these things are kind of the fundamental definitions of these states. Solids have a definite shape and a definite volume. Liquids have a definite volume but no definite shape. and gases have no definite volume and no definite shape. They fill their container. Usually, for most substances, as we go down this list, they get bigger. Now, we were talking about water, and it's an exception for water. Actually, I'm sorry. As we go down this list, they get bigger. Yeah, that's right. For water, actually, the solid takes up more room than the liquid. Solid water, ice, takes up more volume because of something called hydrogen bonding we don't need to worry about right now. Solid water actually loses volume as it melts. For most things, this gets bigger as we go down this list, called thermal expansion. That was one of your vocab words. Thermal expansion. As things get warmer, they get bigger. The opposite of that is thermal contraction. As things get colder, they get smaller. And we have this, as the energy changes, we have this heating curve here, which I want to show you. I'm going to step over my little puddle. You see this heating curve here? You'll notice if you look with me at this on the video or in your book on page 480, there's this chart that has the temperature on the y-axis and the heat on the x-axis. As, excuse me, as we add heat to it, you'll notice at segment B and D there, the temperature doesn't change. That's what I was talking about before, where if there are both solid and liquid in one place, they must be that temperature. So until all of, for instance, at point B, or at line segment B, until all of that solid has melted, until all of that solid becomes a liquid, the temperature doesn't increase any. Does that kind of make sense? Basically, while they're both there, it has to do the job of getting all the solid melted before it can start increasing in temperature again. Does that kind of make sense? If both of these two are in one place, they must be this temperature. If both of these two are in one place, they must be, what temperature does this happen at? I forgot to put boiling point. For water, it's 212 degrees, but that's also the condensation point. That's the temperature where if we have gaseous water, if it gets down to that temperature, it will start to condense as a liquid. So these temperatures are where that phase change happens, that state change happens. And by the way, I will alternate between saying phase and state for this, but they're the same thing. A phase change or a state change. These are phases of matter. They're also states of matter. What about plasma? What about your boy plasma? What's special about him? We're adding more energy. These particles are bouncing. If we add so much energy, what happens? Do you know what happens with plasma? You say explode, but what's happening is they get so much energy that the electrons are stripped away from the nuclei of the atoms. The atoms, we say, ionize. The electrons are stripped away, and now it's behaving as electromagnetically charged stuff. The atoms ionize, it now has an electromagnetic charge. Which of these do you think is the most common in the universe? It's kind of hard to say which one's the most common on Earth, but which of these four states of matter do you think is most common in the universe? It is plasma, Cody. Why do you think? What in the universe is plasma? No, not space.
Cores.
I'm sorry, what? No, they're not. Good. That's a good guess, though. A big thing about space.
Oh, all the atoms.
No. No. Okay, the sun and the other stars. The sun and stars that make up almost the entire mass of the universe are in the plasma state. They're hot enough. They have so much energy that the atoms are separated from their nuclei and their electrons separate, and they behave as plasma. That's true of the universe. The most common state of matter in the universe is plasma. We're going to talk now. We have 3 maths and 3 additional concepts to talk about, and the first 2 have to do with fluids. So let's write down. I'm going to do that over here. Let's write this heading of fluids. Fluids flow. They are usually, we consider them to be gases and liquids. When your doctor says you need to drink more fluids, he does not mean both gases and liquids. In medicine, fluids means basically water, maybe juice. But in physics, fluids are anything that flow, which include both gases and liquids. And we're going to talk about those 2 right now and separately. We have this idea of buoyancy. You did a lab about buoyancy, yeah, with your ice cream. Liquids offer buoyancy. Really, so do gases, but we usually talk about specifically with buoyancy, with liquids. And this is where objects displace, I'll put fluid and either float or sink. What determines whether an object floats or sinks in a fluid? Yeah, if it compared to its volume, compared really to the volume that it's displacing, how much mass it has, whether it's heavy or light. And that, you rightly say, someone, is its density. Rho. Rho is density. If rho of, we'll put rho of the object is greater than rho of the fluid, what's going to happen there? If the object is more dense than the fluid, the buoyant force will counteract it a little bit, as we saw in Lucas and Cody's lab, but it will still eventually sink. If the reverse is true, if rho of the object is less than rho of the fluid, it will float. The buoyant force will overcome its weight. Two little buckets, two little balls. In this one, in the sinking one, the weight is greater than the buoyant force. In this one, the buoyant force is greater than the weight. Does that kind of make sense? Every fluid offers some buoyancy. Air is a fluid. Where's my balloon at? I really got a mess going on here, but I need another balloon. I got a broken balloon, I got paper towel, I got coffee mess. So in the beginning of the year, we said these two objects will fall at different rates because what? This one's lighter? No, that's not right. Remember, it has to do with what? At the beginning of the year, we said the air resistance, right? And now we're redefining that as buoyancy. It's the same thing. They're the same thing. They're different names for the same horse. This one, because it takes up more volume compared to its mass, is given more buoyancy by the air around us. Remember, we're living in a fluid. We don't live in nothing. We live in a fluid called air. More buoyancy compared to its mass, less buoyancy compared to its mass. Both of them are going to sink, right? Both of them have greater weight than buoyancy, but this one will sink faster. This one will fall faster because the air offers it less buoyancy because its volume and its mass. Oh, just like I said. The same thing would happen. A similar thing might happen if we were in water. I think this would sink and this would float, right? Because in this case, the buoyant force would be greater than its weight. It would float. And that's kind of what's happening with this balloon or helium. The air's buoyant force would be greater than the weight of the balloon, and it would start to go up. It floats. Okay, questions about buoyancy? I don't want to pop this one. I really do want to pop this one, though. Your book goes on to talk about Bernoulli's principle, which has to do with the motion of fluids and the lift they generate. You'll have to read about that on your own because we're running out of time. I'm going to erase this. Does anyone still need these things about states of matter? Yeah. Yeah, good job, Miranda. I'm sorry I caused you to have a job during when you were supposed to be learning. I really thought that would be a lot easier to find than it was. Let's talk about the two kinds of math that we're going to do. We'll probably only have time to talk about one, and that is pressure. If we do run out of time, we will talk about, in fact, this is almost definitely going to happen. We'll have a part 2 for this, and we'll talk about the gas laws tomorrow. Pressure is force exerted over an area. And the math is very similar. P equals F over A. Make sure it's capital A, where P is, guess, pressure. Where F is, guess, force. And where A is area. How do we measure area in the SI? What's the SI unit for area? It's length times width, so what units would we use? No. In the SI, meters. So square meters. Yes, meters squared. What do we use to measure force in the SI? We talked about this earlier in the year. Newtons. So pressure is a Newton over a square meter, which equals, we call this a Pascal. Capital P, or lowercase a, is a Pascal. It's a very small unit. A Newton is a very small amount of force, and a square meter is kind of a large area. And so we usually use kilopascals, which are thousands of pascals. But this is how we calculate pressure. This is how we calculate pressure. We were now at this point going to talk about the gas laws, but I don't think there's time. There is 1 minute, and so we'll talk about that tomorrow instead. And this and the gas laws will be your math for the chapter, and the stuff that we just got done talking about before that will be your concepts for the chapter. Do you have questions at all? Hi, I miss my coffee.